Okay, let's look at the conversion problems in slide 53. These are dimensional analysis problems when they're a little more involved than the first ones that we saw earlier. So let's do problem 1. What is the area of an 8.5 by 11 inch paper in centimeters squared? It's problem 1. I have an 8.5 inches by 11 inches sheet of paper, and I want to calculate the area in centimeters squared. Now, if I do this calculation, I should get 93.5 inches squared. Now, I'm not going to cut this off rounded yet to the correct number of significant digits, because if you round after every step, you will get a large error. So we'll round at the very end. But you should get this particular number. So now what this tells me, the inches squared tells me, is that I have 93.5 inches times inches. That's inches squared. So to convert it to centimeters squared, or centimeters times centimeters, I have to convert each inch to centimeters. And I do that by knowing that 1 inch has 2.54 centimeters. So therefore, to convert this to centimeters twice, I will have to write my conversion unit in such a way to get rid of my inches. So my inches have to be at the bottom. 1 inch, 2.54 centimeters. And this will cancel my first inch, but I also have another inch, which means that I will have to repeat this. I have 2.54 centimeters for every 1 inch. And now this takes care of the other inch. And what am I left with? Centimeter times centimeter, which is centimeters squared. So if you do the calculation, you should get, and I've already rounded it up, but you should get 6.0 times 10 to the second centimeters squared. Okay, and this is now reported in the correct significant digits. Note that, and I mentioned that in lecture, but note that we don't take these into consideration when we do significant digits, because these are considered exact numbers. So anytime you have those numbers in the conversion factors, don't count those. You only count the numbers that you start with. So not conversion factors. They do not figure into figuring out significant digits. So because 8.5 and 11 both have 2 significant digits, and I'm multiplying throughout, that means that my answer should have the same number of significant digits as the one that has the least. And because these both have the same number, which is 2, my answer will also have the same number, which is 2 significant digits. Now let's look at the second problem. The gas tank of a certain luxury car holds 22.3 gallons if the density of gasoline is 0.8206. So I have a volume of 22.3 gallons. And then I have a density of 0.8206 grams per milliliter. Determine the mass in kilograms and pounds of the fuel in a full tank. So mass in grams and in pounds. I have to figure that out. Okay, so let's start with what am I given? I'm given a volume and a density. So my first thing that I need to do is convert my gallons into liters so I can have the correct units with a density. Okay, so if I take 22.3 gallons, 22.3 gallons, I want to convert that to liters, which means that I want liters on top and gallons at the bottom. So liters up here and gallons at the bottom. My conversion factor is 3.78 liters there are 3.78 liters in 1 gallon. My gallons will cancel, and I'm left with liters, which turns out to be 84.29. Once again, I will round at the end. That's my liters. Okay. Now, remember that my mass, so density is equal to mass over volume, which means that my mass is equal to density times my volume. This is my volume. This is my density, which means that if I multiply my volume times the density, I should get my mass. So if I multiply by 0.8206 grams per milliliter, I should get my mass in grams. However, I need one more step. This is in liters, this is in milliliters, so I can't do it directly. I have to convert my milliliters to liters first, which means that I know that 1 liter has 1,000 milliliters. So my liters here will cancel with the liters here. My milliliters will cancel with the milliliters, and I'm left with grams, which is what I wanted. I wanted here a mass in grams. So if you do this math, you should get, and of course I did that all at once, but you should get 69,200 grams. Okay, so now I have the mass in grams. It wants me to convert it to kilograms because, I'm sorry, I actually wrote it wrong. It wants me to convert it to kilograms and to pounds. I have it in grams, which means that I have to convert this to kilograms. If I multiply, so this is my conversion factor, 1 kilogram has 1,000 grams. That means that this will give me, divided by 1,000, 69.2 kilograms. Okay, and if I look at my conversion factors, or my numbers that I start with, this has 3 significant digits. This has 4 significant digits. Because I'm multiplying throughout, my answer should have 3 significant digits, and it does. Okay, so now I have 69.2 kilograms, but I want to convert it to pounds because it tells me it wants it in kilograms and in pounds. Okay, well, now that I have it in kilograms, there is a conversion factor that converts from kilograms to pounds. So I need pounds on top, and I need kilograms at the bottom. And the conversion factor is 1 kilogram has 2.2 pounds. My kilograms will cancel, leaving me with pounds. And if I do that correctly, it would be 152 pounds. Once again, with 3 significant digits. I don't count this because this is 2.2. This is actually a conversion factor, so the numbers in there are considered exact. They don't enter into the significant digit tabulation. But 69.2 has 3, so the pounds, this answer should also have 3 significant digits, and it does. So it has 152 pounds. Therefore, a volume of 22.3 gallons that is completely full of gasoline, so a tank that has 22.3 gallons in it, with a density of gasoline being 0.8206, will weigh just the tank, basically the gas in the tank, without the tank, but the gas will weigh 69.2 kilograms or 152 pounds altogether. Let's look at problem number 3. As an instructor is preparing for an experiment, he requires 225 grams of phosphoric acid. So mass is 225 grams. The only container readily available is a 150 milliliter Erlenmeyer flask. So my volume is 150 milliliters. Is it large enough to contain the acid whose density is 1.83 grams per mil? So my density is 1.83 grams per mil. Okay. is this flask large enough? Okay, there are two ways that I could do this. I could take the volume times the density, figure out the mass, and if I have less than that, then that means no. If I have more than that mass, that means that I have enough. Or I can find the volume from the mass and the density, which that is what I'm going to do, and then compare it to this density and see if it's smaller or larger than that. But I know that my density is equal to the mass divided by the volume. So to figure out what the volume is, I multiply, To figure out the volume, I can first multiply by volume both sides. Okay, that isolates the mass. And if I want to isolate just the volume, I also have to divide by density both sides. My density here cancels, so that means that the volume is left or is given as mass over density. Okay, now that I have this, I can say my mass is 225 grams, so 225 grams divided by my density, which is 1.83 grams per milliliter. My grams will cancel, milliliter will come up on top. And if you do this, it will be 123 milliliters. So that is the volume required for this mass to be dissolved in. And I have an Erlenmeyer flask of 150 milliliters, which means that yes, I can use this flask because the volume that I need is smaller than the flask. So that is the answer to problem 3. I will once again erase this, and then we will finish up with the last slide, those problems, after this.